So, welcome everybody to the 11th lecture of wireless communication course. In today's lecture, we will be talking about diversity techniques. So, in the previous, up until now, we have given you an overview about the wireless systems. Then we discussed the channel properties and channel models. We studied them extensively. And then after that, we studied modulation schemes and their performance metrics and how to measure its performance in terms of bit error rate or simple probability of error. And then we studied the fundamental capacity limit of different types of wireless channels, starting from flat fading, frequency selective, with different cases. And finally, in last lecture, we studied the impact of channel on the performance of your system. For example, we studied the effect of fading on the outage probability of your scheme. We said that when you have fading, you have outage. Besides, we studied the effect of intersymbol interference and how does it affect the bit error rate and gives you error floor. No matter what you increase the transmit power, you will have a certain error limit that you cannot improve it more. So these impairments of the channel must have some solutions. I mean, because if we leave them as they are, our system will not perform well, and the performance will not be up to the expectation of the customer in terms of quality of service, capacity, bit error rate, latency, reliability, security, all these parameters that we mostly care about. So therefore, in today's lecture, we will study one technique, one concept that can help mitigate the effect of fading in wireless channel. So if you employ this concept in your design at the transmitter or at the receiver, you will be able to mitigate the effect of fading in your channel, in your system overall. So basically, one can notice that the structure of our course. First, we studied the channel, we understood it, we understand then its impairments, obstacles, and then we try to optimize the transmitter and receiver. Now your goal is to design the transmitter and receiver with the knowledge of the channel you have in such a way that you send your message with minimal effect by the impairments of the channel. So based on that, the outline of our lecture is going to be as follows. First, we will study the diversity concept. When you hear the term diversity in wireless communication, you must be able to say, what's this? Then we will explain two types of diversity: receive diversity, transmit diversity. At the receiver side, diversity can be in time, in frequency, in space, or in angle. All these dimensions, you must understand how diversity is applied on. The same with transmit diversity. After that, we will have a look. We will give you examples on each domain. Time, for example, give you an example on diversity technique that utilizes time or utilizes frequency or space or angle and so on and so forth. Then after that, considering that you have a system that provides you with diversity, then how to make use of this? How to make use of this in such a way that you improve your performance by using technique that like selection combining, equal gain combining, maximum ratio combining, and interference rejection combining as well. So basically this is what we will be learning and knowing in this lecture. So what's the basic concept of diversity? Diversity, as the name implies, most of the names that we come up with in wireless communication are related to the common famous terms we use in practical life. Diversity means sending your signal in a way that you receive it from different sources. You send the same signal, your signal, over independent fading paths, or receive your signal from independent fading paths. Focus on the word same. If the signals are different, then you cannot make use of diversity. So basically the term I'm putting here / send same signal over independent fading paths or receive same signal from independent fading paths. This is what diversity is in wireless communication. Now, what's the point? I want you to think with me. What's the point? What will happen when I send the same signal 2 times or 3 times instead of sending it 1 time? You must understand this. Now I have a transmitter here and I have receiver here, and you have fading channel here. When you send it 1 time, there is a probability that the packet that experienced this deep fade, you will not be able to receive it at the receiver. Is that right? But when you send it at from another path, where the channel will have different realization, different response, like instead of having this channel, you can have this channel, completely independent. So what's the probability that you face this deep fade? Instead of having a probability 1, you have now half. Imagine you have another 1. The probability, as you increase the number of paths, the probability of experiencing deep fade reduces. And if the probability of experiencing deep fade reduces, then your overall performance increases. Your outage decreases. Let's say now one smart student can say, okay, what if I have infinity number of paths? When you have infinity number of paths, you have 0 probability of making errors. And when do we have that? Joel, you know this answer from the previous course we talked. Give me a technique that can provide massive amount of paths so that your channel become hard, which means has no fading. 5G course in 5G, massive MIMO. This is massive MIMO. Massive MIMO, you send the signal from different antennas, same signal, or you receive your signal from different antennas. When you combine them, since you have more than 20 paths like this, imagine, keep putting 20. What's the probability of having an error in this? 1/200 almost. I mean, the probability of making error so little. Instead of being 1 to half, to third, to quarter, to 1/5, to 1/6, it's 1 in 200. So this means that the more path, but of course there is a trade-off. This comes at the expense of something. You got the concept? Send the same signal over independent fading paths, or receive the same signal from independent fading paths. So from your understanding for the wireless channel, can you give me an example of receive same signal from independent fading paths? Yes, you can give me. For example, when we have delay spread, the delay spread happens because of multipath. You send your signal here, which is here actually in the first. You send your signal here. This is your signal, and you receive it at different times. This is the first. This is the first signal. This is the second, third, fourth. All these are carrying the same information actually, but you are receiving them at different time instances. So if you design your receiver intelligently, you can harvest the energy from all these paths. When you harvest more energy, you increase the signal to noise ratio. You increase the quality of your received signal. Where if you don't have multipath, you just receive one path. So there is no redundant paths to protect your information. So you tell me, I give you one example of received diversity, which is multipath diversity. Multipath when you have frequency selective, and multipath when you have Doppler channel. For example, when you transmit your signal, and because of the movement in the channel, you receive it at different frequencies. So it's basically the same signal, but you are receiving it at different frequencies. F1 plus delta F, F1 plus delta F2, delta. This is also diversity. We call the first type of diversity multipath diversity. The second one, we call it Doppler diversity. We also have angular diversity. time dispersion, time dispersion, which is frequency selective, which is due to multipath diversity. Multipath gives you that. While time selective, which is related to Doppler, gives you Doppler diversity. Now these are two examples for received diversity, but we will study them in more details. Now I was explaining them by this, but this is basically a good drawing where you can see this is the first fading path, the red one, and this is the second one, the blue one. Do you see with me the blue one? So as you can see, they are independent. At the time when the blue one is in deep fade, see this, the quality, the amplitude, this is time, and this is this axis is the amplitude of your channel. When it's really low, this means that the amplitude of your channel is very low. So when you send your data over this channel, what happened? The channel acts like a filter. It suppresses it. Yes? When you multiply, for example, 5, let's say this value is 5, and multiply it by the value of the channel here, 0.01. What's the resulting value? It's multiplication, yes, convolution in time, multiplication in frequency. When you send your data of amplitude equal to 5, means very high power. And it faces deep fade. The deep fade, the amplitude of the channel, 0.01. When you multiply them with each other, the resulting value becomes so small. So this is bad. We want to avoid that as much as we can. When we send the data from a different path that's independent, there is a probability that you get better channel gain from the second path. So if you couldn't receive your data from this path, you can receive it from this path. You understand why it's diversity? But this is not guaranteed diversity. It's statistical. Depends. Sometimes you might get two bad channels. You send it from two paths, but still you are getting bad performance instantaneously, I'm saying. But statistically, when you get all the random values and average all of them, you must get some improvement. And usually we measure the performance of wireless channels statistically. So with this explanation, we can now understand the advantages and merits of diversity. Smoothes out deep fades, means reduces it. Did you understand how? If I ask you how, you understand the concept, how it reduces it. Level crossing rate will be lower. What does level crossing rate mean? See this channel? Let me clear these. See for example, this channel, yes? If you put here a threshold, anything below this, we call it what? Level crossing rate. Anything below this, we say it's deep fade. And how many times this happen within the duration of the channel or within the duration of your retransmission? You count how many times. Let's say if your channel is really frequency selective, highly frequency selective, you will have too many of these deep fades. Yes? So how many times you experience these deep fades within a period? This we call it crossing. We call it level crossing rate. So when you have diversity, you reduce this rate. This means that your overall response almost constant. Yes. Fade duration is reduced. I explained this. Your extreme case is, for example, when you have 200, 500 antennas, with the probability of experiencing all of them redundant and substituting each other, which means that you have lower probability of being in deep fade. If interference rejection combining, it allows for better reuse actually, and therefore increase the capacity of your channel when you have really robust channel which is not affected by the fading in your signal. Everybody also must know and remember why fading happens to be able to solve. Since we have fading, we have two ways to solve it. either to adapt to it, cope up with this problem, or try to reduce it. This technique, diversity, reduces it. And it can really eliminate it if you use massive MIMO. Somehow, not perfectly, but to a huge certain degree of freedom, you can really reduce it significantly. Now, what are the diversity techniques we have? Now I understand as a communication engineer, wireless engineer, I understand what diversity is. I know how to increase it. I know conceptually how it reduces the level of fading in your overall performance and how to get much better bit error rate or enhance the reliability. Now, how to have it? You need techniques to have it. So these techniques are classified according to the signal domain. First, we have diversity techniques in time, we have in frequency, in space, in angle, in polarization, in sight. Let me explain them to you little by little. Time, you send the same signal at different time instances. This is the basic definition of time diversity. Example of that, in wireless communication, we use what's called ARQ, automatic repeat request. This is in all the standards, even in Wi-Fi, in all computer networks, in all wireless networks, in all LTE, 4G, 5G, all of them. They cannot live without ARQ. What ARQ says? ARQ says the transmitter, when the transmitter sends a packet to the receiver, this packet can experience deep fade, too much interference, it can have some impairments. And this packet is very important for a user. Like suppose this packet contains your email. So can you tolerate this, or you are uploading a file? If the system design says if your receiver if the receiver doesn't feed back an acknowledgement that he receives the packet within certain duration, then resend the same packet after a certain period of time. Now we all know from wireless channel knowledge that at different times the channel give you different responses. So most probably if this channel was not received correctly because there was a huge interference or too bad fading during this time instant at T0, at this time T1 we might have better channel like this instead of having channel like this. So the system design says you must keep retransmitting your data packet until you receive it correctly, or it exceeds certain limit of delay. Your system cannot support more than this delay. Depends on the application. If you are transmitting video and one frame is dropped, you are allowed to retransmit 3 times maybe, but not more, because video cannot tolerate delay. Voice, you are allowed 2 times. But if you are sending message, you must keep retransmitting message, because message is delay tolerant. SMS, email, whenever it reaches, but I must receive it 100% correctly. I cannot read half email. Yes, I cannot read that's the difference between that's why we need adaptation in our system design. For example, if you are on a voice call, do you tolerate delay? Okay, wait for me to send the packet 3, 4, 5 times. You have no tolerance. Quickly, I allow you 1 more time to send it. If it didn't reach, it's okay, but carry on. Oh, okay, what did you say? Then the customer your friend repeat 1 more time because the quality of your voice was bad. So you become part of the system design. The customer himself repeat what you have said 1 more time. Yes, you got it? If the system is not able to repeat it because of delay constraints, then your friend tells you, I couldn't hear you. You lost the internet connection or the quality is bad. Then you repeat again or spontaneously. This is something in our nature. So we try to do this with the system. If the system doesn't satisfy your requirements, then you must repeat this yourself. So this is ARQ. Everybody understands what ARQ is? Automatic repeat request. You repeat the transmission of your packet automatically. Frequency. How do we do that in frequency? Frequency hopping spread spectrum. In GSM system, everybody knows what GSM is? GSM, the mobile, the first phone that started calling digitally back before 10 years. It was a revolution when people started using phones for calls. Now you are not appreciating that, but it was really a revolution. Now voice is for free and this. In that system and many systems after that, they used to transmit, for example, this is your data, your symbol. You transmit it over F1 and then it hops to F2, F3, F4. It keeps hopping. Why is this? Because the network was designed in such a way. In this area, you use frequency 1. In this area, you use frequency 2. In this area, you use frequency 3. And you keep repeating to serve more customers. We will talk about how to serve million users by 2 megahertz bandwidth. Can you do this? This is a challenge in wireless scheme because 2 mega, practically, theoretically, can serve only 100 users. But your country has 20 million users. How can you serve with 2 mega, 2 million? This was extremely challenging before, at the time of transmitting digital wireless systems, GSM, the second generation we call it. Now we are 5G and people starting working on 6G and preparing techniques for that. That was 2G. Now to solve this problem, because now since we have many different channels, and you repeat the use of the channel at different locations, then they interfere with each other. Because of interference, sometimes the interference is so bad in one of the channels. So to avoid that, look at it like fading. To avoid that, but not in time and frequency, to avoid that, you just keep jumping. So when you keep jumping over all the frequencies, your performance will get averaged. Instead of being locked to one extremely deep interference channel, you get just 1% of the extremely bad channel and 1% from the good, 1% from the middle one. Then when you average, you get high quality. This is the basic concept of frequency hopping spread spectrum. As the name implies, frequency hopping spread spectrum. You keep hopping over different channels, and therefore your performance is the average of all these frequencies. Space, with the advent of technology of MIMO, you have 2 antennas or more. You transmit your signal from here and also from here. So each antenna, since the spacing between the antennas usually more than half wavelength, it's greater than lambda over 2. This means that the channel that the first antenna experiences is different than the channel that the second antenna experiences. So due to these differences, you have more chances of transmitting your symbol correctly. Instead of the more antennas you use, the more reliable your communication can be if you use them for diversity. Angle, the same. For example, your receiver is here and he has directional angle or something. Instead of keep receiving the signal from one direction, this direction might be blocked, might be bad, might be not good. Your signal is reaching, but from here in a very good condition. So why don't you get that signal, or get that signal, or get that signal? So it's based on the angle. You receive your signal from different angles. Polarization. Everybody knows polarization from electromagnetic. Yes, polarization. What's the definition of polarization? Is the direction of the electromagnetic field in your electromagnetic wave. The electromagnetic wave is composed of electric and magnetic field. The direction of the electric field is very important in communication because this is what we simulate practically. And even in your simulator network, and this is what you simulate, the electric the electric fields. In MATLAB, when you simulate your system, what do you simulate? Do you simulate the electromagnetic waveform? Not really. In CST, you simulate electromagnetic wave. You see it because it's important for antenna. But in MATLAB, we simulate the voltage, the current that produces the electric field. And we usually have many types of polarization, but we have linear polarization, we have circular polarization, we have elliptic polarization. But one of the techniques to improve your system performance is, instead of sending your signal with vertical polarization, you send it with both vertical and horizontal. So if your signal, now this is very deep. There are, I hope you can visualize this. Now polarization, the richness of polarization, the richness of receiving your data polarized depends on the multipath on your channel. For example, let's say you are in a millimeter wave channel. Millimeter wave, what's the characteristic of millimeter wave as we explained in the previous lecture? What we said about millimeter wave? You can pluck it by your hand, it cannot penetrate the wall. What does this mean? You don't have too many reflections, strong reflections, especially if you are far from the receiver, outdoor. Indoor you might get, because the distance is usually, when it gets reflected, still relatively close, you can detect some. But if you are outdoor, you hardly receive few reflections, or you might not. Anyway, now you send your signal with vertical polarization. Yes? Now, suppose your receiver is horizontally polarized. Now, to be received by the receiver, you must make this aligned with the horizontal so that you can induce current from your antenna. Otherwise, you cannot introduce current. It has to be aligned. Now, in millimeter wave, this is a problem. If your transmitter and receiver don't have really the same polarization, you might not receive your signal, although your signal is reaching the receiver, and you might get confused. There is signal, but I'm not receiving my data. Why? Because the signal, because of the polarization. The channel is not rich, doesn't have too many reflections so that it gives you all types of polarization. Just what the polarization you use at the transmitter, you see at the receiver. And if you are not using the correct polarization, you lose your data. Well, for multiband channel, like the current channels we are using for Wi-Fi and LTE, 4G, 3G, you send your signal, the signal is rich of multipath. By the time it reaches you inside 100 of multipaths. So from these 100 multipaths, when you send with vertical, this vertical becomes horizontal by the time it reaches the receiver. At least half of them. Because the channel keeps changing the polarization. How the polarization changes? Basically the incident angle, the reflection angle, the inclination angle. This is due to the environment and characteristics of your medium. So by the time here, that's why in 2G, 3G, 4G, we don't care much about polarization. We transmit it, and of course we receive it. But we really care much about millimeter wave when you don't have too many reflections, and you must be careful about that. Now, longest story short, I have given this comprehensive introduction about polarization, but the point that I want you to make is you can enhance your performance by sending the signal not only from the horizontal polarization, but also with vertical polarization. Think of this like using sine and cosine. Cosine and sine, they are orthogonal to each other. Means you can send your data on top of them and make them fully overlap while they are perfectly orthogonal. If they are orthogonal, they are causing zero interference to each other, and you can separate them nicely at the receiver. That's why in wireless communication we love orthogonality. because orthogonality means zero interference between independent channels. Can send more data or enhance your performance while not having too much interference. The last type of diversity technique, we call them site polarization. Site diversity or position diversity. You have usually in wireless communication system, what do you have? What do you have in wireless communication system? You have multiple base stations serving the users. Yes, is that true? You have, for example, one base station serving the current user and another base station serving another user. For example, this is base station 1, this is base station 2, and there is a user here. Now we know as the user moves away from the base station, the path loss decreases and the path loss increases and the interference also increases from the other cell. So in that situation, you are desperately in need of something that enhances your performance because you are in a very bad position. Like this is dead zone. This is critical position that not everybody wants to be in. When you are in the edge, this is the cell and this is another cell, and you are user here moving and you reach this position, you stop the car, you are trying to do, and the quality here from any of these base stations to this is really bad. So what the base station agree among each other that let's share the data of this user among us and send it jointly. So this receiver receives his signal from both this base station and this base station jointly. So this has different fading and different performance, different interference, and this has different interference, different fading. So if this was bad, this might be good. If this was bad, this might be good. But so your probability of making error reduces. Of course, you can have another base station collaborating with the user, with these base stations, and share the data of the user and send it to him. So he gets 3, 2, 5 links. And this ensures that the receiver who's located in a very bad situation and not able to receive his data correctly from single base station, now he can jointly receive all these signals all together and amplify his signal to noise ratio, and therefore reduces the outage. So what do we call this in 5G, 3G, 4G? We call it COMB. Not really combination, it's abbreviated for cooperative multipoints. Multipoints, this is multipoints, point 1, point 2, point 3. And they are cooperating among each other. This is what we call it. Now, did you understand these things? Now, the one who understands these things, at the time of the exam, for example, he doesn't need to go over this material. See? And I don't tell him to go over the book. See, this is the point. This is the beauty of attending the lecture. This is the beauty of attending the lecture. I don't tell you the first 4 chapters of the book because you are asking me what's the material, and I didn't see you in the class. So of course, I will tell you the book. Yes? So instead of understanding concept like this in 5 minutes, you go and try to study it in 1 hour, 2 hours, and not sure you can study it. You don't get the fruit. Here you get the fruit. You just need to. The other information, for example, is really all of them about the same concept, the same thing. But here I'm putting it for you so that you, at the time of the exam, for example, if you want to review or get more information, you can at least remember more with the information I'm giving here. But here, for example, site diversity. What I'm saying here, cooperative multipoint, advantage multipath, each one is different multipath, different shadowing, different interference, and you make them, since they are independent, you reduce. Even I talk more than what's written, of course, always, that's the case, but you must combine both. Your notes, your reading from the lecture, Plus, when you have time, go to the book and see, because books always improve your understanding.
I have a question.
Yes, one question.
What's the difference between sight and antennas? Sights.
Yeah, the sights and antenna. What's the difference between sight and antenna?
Because it's the same principle.
Yeah, but both of them are, you can say, space diversity. The same principle. What's the difference? Tell me. What's the difference? He says, good question. He says sight and antenna look similar to each other. So what's the key difference? The key difference is when you are in the same site and having two antennas, you might have different instantaneous fading, but you don't have different path loss or different interference or different shadowing. Yes. Yeah, sight gives you total independent channel in all the measures, in fading, not only in fading, in shadowing, in path loss, in interference. For example, between this and this, you might have one building. Between this and this, you might have three. Who knows? Geographical area. That's why the sight is sometimes more powerful than having two antennas. Plus, just recently, I was looking on the literature. I found something called instead of we have massive MIMO, everybody knows. Massive MIMO, the best thing you can do with massive MIMO is to form beam with extremely narrow width. So, but unfortunately, you have always this here. You have this energy not utilized. You just care about the tip or here. Now, there is a technique in the literature that you can make these sites collaborate between each other, or antennas. They can be dummy antennas actually, but the most important thing, they are not in the same site, not in the same location, not on the same base station. They must be distributed and far from each other. They can be just single antenna, and you have your processor and server in your home. You know what you get after you do proper processing? You get just your signal available around the user. Imagine there is the signal, this is like magic. You provide a signal here without having a beam here. There is nothing here. You see spot of your signal available in this location only around the user. How did it reach here? It was here actually, but they design it in a clever way, in such a way that the signal here gets cancelled due to the other signals coming from the other antennas distributed in different positions, and you get only a spot of your signal in a certain location around the user. So this is extremely amazing. I mean, the interference problem that we always have, and it's limiting our performance, you are totally eradicating it, removing it from your system. This, I have never seen such a design in my whole life. To have a signal only around the user, following you, around you, and you don't seem to have this signal coming with beam from the base station. Everybody knows from antenna, you have the antenna and reduces patterns here around it. To reach here, you must have pattern here. Is that true? But imagine that this pattern get cancelled. This is how I explain it to you. It's of course impossible to have only the signal there. It's actually the signal was here, but it's now removed due to other signals appearing, the interference coming from other. And you have it only around the location of the user. We call this technology what? DIDO. Instead of MIMO or MIMO, distributed input, distributed output.
Why would you want to cancel this?
MIMO, multiple input, multiple output.
Why would you want to cancel this?
Because interference actually. You have other users who are located in this location. If you don't cancel your signal in that location, it will appear as interference to those users. Each user must get his own signal not the other user signal. Yes, he says why the signal should not be here. He says, I mean, he says in normal system, we have this beam formed from the base station. And usually the user is here. Now he says, why should we remove this signal? Yes, this pattern. Yes, you are saying this. Because there are other users here, most probably, and they want to get their signals. No, for example, what if there are other signals? It's dense area. Other signals here. Your user is here and your base station here. How can you be sure that there are no users here? This means that you are not allowing any user to become here so that you don't interfere. So if I want these users to be here and get their own signal, I must remove this part of the beam that was intended for this user, so that this user don't see the signal of the other user. Got it? Makes sense? And what's the consequence of this? You can increase the density of your area. Instead of having only 1 or 2 users, you can serve them properly. You can put 100, 1,000. This is magic. This is literally, if you know wireless and see this, because since you don't you are new to wireless, you don't know how exciting this to be able to do. I mean, even now in the wireless, if you are not up to the literature, you won't believe this.
Security reasons also.
Yeah, this is good for security also. That's what I gave my undergrad student. I told him, look, this is a startup company actually. They only published one about this, and it's patented, and they make a company out of it and selling the product for Nokia. And the guys like you, master students actually, they just joined an incubator and came up with the idea and prototyped it, and then made a product, successfully tested, and then partnered with Nokia, and Nokia is selling the product for them, and they are actually selling it internationally. I was really very, very amazed of this technology, but it's not famous in the academia because they didn't publish. Usually, if the technique is really good and the people behind it, they want to make money out of it, they don't care about publications. They don't want to have prestige or this. They want real practical business life. So I only found one paper and read that paper and really got too much excited. They call it P-cell. P-cell means personal cell. Personal cell, your signal is always following your phone. So in an area of 1 by 1 meter, you can put 16 phones back to back, and everybody gets full bandwidth. The other advantage of this, that's the exciting point as well. You get the full bandwidth. In traditional wireless communication, you divide your whole bandwidth that you buy from the government for $5 million or $10 million. You divide it so that you can serve more users in different locations. But what happens when you divide your bandwidth? Each user gets only a share from the whole bandwidth, 10% of the whole bandwidth. So the data rate overall gets reduced, because you are getting 10% of the whole bandwidth of the system. But with P-cell technology, BDO technology, you are getting each phone is getting the full bandwidth of the system. Why? Why he's allowed to get the full bandwidth? Because there is no interference.
Dedicated line.
Yeah, dedicated to you. That's astonishing. In wireless, this is astonishing. I don't know how we ended up discussing this, but this is only because of discussing comp and site and the importance of sending signals from totally separated location. We call this technology distributed MIMO, or distributed input, distributed output, or MIMO network MIMO. They are really separated. It's related to comp and this. This is very exciting. I hope this helps you also at least teaches you that there is a groundbreaking technology that's gonna shape the future. I hope you feel the importance of this. You know the difference between this science and computer and the programming and the other available things in the internet. Usually the other programming, they are not difficult. Mostly IT related fields. Anybody just learns them and just start implementing and doing. Unless like there are some black box IT things like how to build data center, how to build this. They don't share this information. Usually they don't share it. But the other things are really available in the hands. When you search on the internet, you have hundreds of tutorial material about this type of thing. But this used to be confidential. Just recently, before 5-10 years, the company is dominating the science of this. And the understanding of this is really a little bit trickier. I don't want to say harder, but treats full understanding, and you experience this in the exam. How these are really, you must understand them in a way that makes you able to think beyond what's there. And this is physical layer. Anything you improve at the physical layer affects all the layers. If you were to improve the data rate in your system to a good level, can you improve it by application or network or this? You can never do this. It's easier to implement and do at the application, but the ground breaking and huge improvements always happen at the physical layer. Although they don't get rewarded too much for that. At the end of the day, Facebook app is a multi-millionaire company, and Ericsson and Huawei and they are not that big in terms of market share. This means that the app that uses the wireless technology makes money more than the technology that served that app. Yes? Now, I haven't talked about diversity technique. Now we need to combine these multiple paths that we receive. How do we combine them? We have the first thing, we call it selection combining. Fading path with highest gain is used and selected. We have maximal ratio combining. All the paths are co-phased and summed with optimal weighting to maximize combiner output signal to noise ratio. And equal gain combining, where you combine the signal coming from all the paths with equal weight. And we have interference rejection combining. At the end of the day, you obtain diversity gain. Now, one might say, cannot we simplify it and explain it in a much nicer way? And I don't want to memorize or look or these things. By drawing. The best thing to explain a thing is by drawing, visualization. Yes, you have, let's say you have received diversity. Yes, and let me assume that the receiver has multiple antennas. Yes, and he receives the signal from all these antennas. This is one signal, this is the other signal, and this is the third signal. Yes. If you understand this example, you don't need to read these. Just focus with this example and you can build beyond that. So the receiver needs to make use of these multiple paths. What's the goal of multiband? What's the goal of diversity? To enhance the performance. But this not only by sending a signal from a different path, the receiver has to do something sometimes, especially if it's received diversity. If the diversity is coming from the receiver, not from the transmitter. So the receiver can make use of this by using different techniques. One technique says, which is this, selection combining. Check the channel response from all the channels and from all the antennas. And the antenna that has the best channel, select it and take your data from it. For example, suppose this is like this, this is like this, this is like this. Which one you select? The one that amplifies your signal. So you just deactivate this and just get your signal from here. So your data will be multiplied by a channel of high gain. So your data total will be high. Now equal gain combining tells you this. Take the signal from all the antennas and sum them. Don't worry about the phase, about anything, just take the signal from here, 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 and sum. This is, we call it equal gain combining. Maximal ratio combining tells you, look, you received signal from different antennas, but these signals sometimes they don't have the same phase. For example, you received the signal with this phase, and another signal with this phase, and another signal with this phase. Now when you sum them up, they don't give you the optimal maximal amplitude. But if you make this, correct the phase of this and put it here, exactly, with the same phase, and this with the same phase, when you sum them up, you get large signal like this. This is maximal ratio combining. It corrects the phases of your received signal and then sum. Because phase is important. If they are not aligned, if they don't have the same phase, they can be added destructively. Their addition does not give you the maximal output. But if you make them all in the same phase, when you draw them in the two-dimensional diagram, this is in the same phase. This is the amplitude of the same channel, of the first channel. This is the amplitude of the second channel, and this is the amplitude of the third channel. When I tell you find the resultant in physics, what do you get? You get a line of this length. But if they have different phases, let's draw another one here. If you have different phases, one in this direction, one in this direction, one in this direction, and find the resultant. Of course, it will, since they are not aligned, the resultant will be much less than this if they were aligned. Did you get it? By visualization, by this. This is what I mean. At the end of the day, when you do these things, you get enhancement to your signal to noise ratio. It will be improved. And the improvement or the gain, we call it diversity gain. And of course, why do we have this gain? Because of averaging the error. Instead of having error probability of 1, when you have 2 paths, you have half. When you have 3, you have third, quarter, this. The more you have, the better. And then diversity gain has changed. Of course, if your system in the exam, if I tell you, you have 2-bit error rate. Yes, 2-bit error rate curve. This is signal to noise ratio. Yes. Which curve has higher diversity? Yes. You have 2-bit error rate curves. Yes, this is the x-axis and this is the y-axis. Here we put the signal to noise ratio. Signal to noise ratio is the power of your received signal over noise. And here the error. We call it the bit error rate. And you draw the first curve was something like this. And the second one was something like this. And tell you which bit error rate curve has larger diversity. This one or this one too? One has more diversity. The effect of diversity to your bit error rate pushes the bit error rate towards the y-axis, which means you can get lower error rates at low SNRs. This is what it means. At low SNRs you get better bit error rate. Why do I need to get bit error rate of low value? Because this improves the reliability of my system. And the reliability is one of the critical performance metric in any communication system. So this is a better curve that explains this. For example, the not bit error rate, outage. This is when you have one path. This is when you have 2, 3. As the point that I want to make, as you increase the number of diversity paths, the slope of the curve becomes steeper. and pushes itself towards y-axis. At low SNR, you get very good bit error rate. Selection combining, combiner SNR is the maximum of the branch. The CDF here, you know, the point here in wireless, it's not only visualization and concepts, we also want to analyze the performance. I want you to mathematically tell me what would be the bit error rate and how to calculate it. To do that, you need to find the statistics of each received symbol from each antenna and then find the statistics of the sum. Now we go back to random probability course, stochastic. What's the probability of the sum of 3 random variables having Rayleigh distribution? Yeah, everybody with me, everybody understanding the importance. You see the example that I gave now? I have 3 antennas, each is receiving the same signal but from different channel. And I'm saying this, in the example, for example, I'm saying this is the Rayleigh channel, the amplitude is Rayleigh. And this is Rayleigh, and this is Rayleigh. Now, you sum them up using maximum ratio combining, you co-phase them, and you sum them. Now, I need to analyze the performance. In the analysis of the performance, the outage probability, what should I do? I must find the probability distribution of the SNR. SNR is mainly the distribution of the instantaneous SNR is controlled by the distribution of the instantaneous fading you have. So how do you find this? You tell me, let's solve it one by one. First, I know that the amplitude of this, A for example, is Rayleigh. Yes. Then the power of this exponential. The multiplication of 2 random variables gives you exponential distribution. From Rayleigh, you go to exponential. And it's the same for all. I go to random probability theory and find what's the sum probability, what's the probability distribution of the sum of 3 exponentially distributed random variables. 3, for example, or whatever. Let's say 3 because we have 3 antennas. What? This goes back to something that's prerequisite for this course. Random probability. Everybody took random probability. You might need to review it a little bit, but at the end of the day, you find out that it's gamma. Now you know the distribution of this new SNR distribution is gamma. Now you put the PDF inside your integration function, the gamma with its parameters, and then you start integrating and finding the outage probability. This is math. I know this is math, and I know that the things behind it is prerequisite to this. Math things. Don't get afraid. Don't confuse them with wireless. That's why you are not allowed to say wireless is hard. I'm talking here about an example where we need the math to support, to find the outage. You understand wireless, but you might have some weaknesses in math that's not related to wireless. I want to make it very clear. You understood the visualization, you understand the concept, you are able to make sense of things and judge. That's perfect. That's amazing. You are now understand wireless. You can design system and this. But if you were asked to analyze the performance, this is what you need to do. If the company tells you, I want mathematically, what's the performance? Don't even simulate it to me. Now, sometimes they ask both simulation and performance analysis, mathematical should be matching, same. So you must have experience in how to simulate the system in MATLAB and how to derive it. And if both agrees with each other, then they say, yes, we believe that. If You provide only simulation, they say it's not enough, he didn't do the math. If you provide only math, they say it's not enough, he didn't do the simulation. When you provide both and show that both they are matching with each other, they are confirming, then this is solid. Because you checked both and both are confirming. Of course, you must make your math available and your codes as well so that people after you can check after you. Yes. So this is the thing. Why do you need the CDF? By diversity, you can get a gain of 20 dB. Anybody can visualize this 20 dB gain? How do you get? For example, let's say at bit error rate equal 10 to minus 3. What 10 to minus 3 means? Each 1,000 packets you are sending, or each 1,000 bits you are sending, you are only having 1 bit in error among all these 1,000 bits. This is what it means 10 to minus 3. 1 over 1,000. 1 error in each 1,000 bits you are transmitting. If I tell you at bit error rate equal 10 to minus 3, how much dB gain you have when you use diversity of order 10? You tell me, you highlight this, you put mark here, and put mark here. This is with diversity 1. And you measure the distance, the dB distance from between this and this. This is almost 2 or 3, and this is 30. 30 minus 2, 28. Around 28 dB gain. You know what this means? 3 dB is doubling the power. So if with 3D, suppose this is the base station, and I can, with certain power B, with certain power P, I can reach here. By doubling the power, you can reach here. By tripling the power, you can reach here. By this gain, I don't know where you can reach. 2, you extend your coverage significantly. This is what it means here in the bit error rate. You don't see it, but this is what it means here. Yes, you extend the coverage of your cell. This is extremely significant for Internet of Things application, outdoor connectivity. When you have diversity, you extend your coverage. With maximum ratio combination, I just said this, you have the signal to noise ratio, SNR, and you need to find the instantaneous sum. It's the sum of all the SNRs coming from each antenna for each branch. It gives you gain of 40 dB, and the distribution of gamma is hard to obtain usually mathematically. Here we say hard to obtain mathematically, but we have another way to obtain it. You know, the way is that you generate your data and try to find distribution that are very close to the available data you measured from the antennas, and the closest one to the data, you say this is the distribution. This is not by math, this is by fitting. Yes, by fitting. For example, I draw my data. Yeah, let me explain to you how to get it. You get here, you get your channel, yes? Here you have values for the channel. It's really, you can even generate it in MATLAB, and here really. You build a for loop, and for each time you generate 3 times Rayleigh vectors, and you sum them. You sum them and plot them, the PDF of them. And then for like 10,000 times to get enough statistics, and average all these 10,000 and plot the PDF of them. Now you get a new PDF, you don't know what's this PDF. Now you go to the standard available distribution functions in MATLAB. You have more than 30 as far as I know in MATLAB. And you start testing one by one. But this PDF, which PDF is the closest to this PDF, to the shape? The one that's closest, then this most probably, the resulting distribution is this PDF. Got it? How to find it? The fitting method. This is how you find it. Now, after finding the distribution, you can find the bit error rate, because the bit error rate is the bit probability of error as a function of the SNR multiplied by the BDF. This is the BDF of the summed SNR, instantaneous, derived with respect to the instantaneous SNR. Now, when you find this, it gets very complicated. Something like this, you need the distribution of all, hard to obtain in closed form, and integral often diverges. When an integral diverges, there is no closed form solution. There is a table, a book called Tables of Integrals. Anybody have heard of this book? Even the ones who specialize in math, sometimes they don't hear about it. But the ones who study communication and go to PhD, for example, on this, they become mathematicians. So basically, in the past, they used to say, good electromagneticians are good mathematicians. And in communication as well, you become, without the intention to be mathematician, you become mathematician. Why? Because the problems you face in wireless, they are beyond the thinking of mathematicians sometimes. And I have seen many professors like in two departments, in the engineering, electrical, communication, and also in math department. Because they know all the math, most of the math sciences, you need to use them when you go into wireless. And I have seen papers like the equation is full page. Never saw this in any books or this. And make sense and interpret it, and it may. So sometimes you get afraid when you see a paper like this. I say I will never ever study communication, especially when I started, like when I was a master's student like you, and saw a paper of all math, like half-page math, and they, oh, how come I can? It turns out that it's really, don't get scared of it. It's all probabilities. And because the distribution is complex, when you put it inside, the integration becomes even much more complex, and things tend to be extremely just series of complex equations. But the thing that's more important than this is to get intuition and interpretation for these equations, and how to link them with practice, and how to design your system to enhance them. So don't get afraid of math. After that incident, when I learned so I close my eye when it's not something to be scared of, math. It's something to explain. Math is an international language. If I put here x plus y equal 10, anybody, regardless of his language, whether Japanese, German, Dutch, Arabic, English, he can understand this. That's why we feel that math is international language first, and it surprises us sometimes with good solutions that you cannot get them intuitively. For example, when I say, let's say, I want to give you this example. When I send my packet this over the channel, by the time it reaches the receiver, it becomes like this. What's the difference here? There is dispersion here due to the channel, and it's cut from here due to the channel. Tell you, please design, I want a system, I want something to add it to this system in such a way when it reaches the receiver, I want it to have it exactly like this. Exactly like this. With your knowledge in wireless, you can never find a solution by intuition to this problem. What signal you will add here so that, or you can make a change here so that you can get the nature will make your packet like this. How can you make it like this? Okay, in math, it's very easy to formalize, to define this problem. I say, what's the extra thing here? It's this signal, yes? Yes, and I want this to be 0. I just go to this signal in MATLAB and define it to be 0. And this is function of what? What made this like this? The channel components. The channel makes it like this, function of this. So the problem turns out h1 plus h2 plus the data is equal, you want to make it 0, force it to 0. So your design problem turns out, what would be the coefficients that I need to put in top of this packet so that when it passes the signal, it becomes the negative of this signal and then it cancels to 0. This is the beauty of math. Makes you able to solve problems that you cannot intuitively solve sometimes, and surprises us with solution, great solution. That's why you must not be scared of math, you must not hate math. It's a tool. A tool is meant to be helpful for you and to solve problems for you. That's it about math. So from now on, your math is your best friend. Don't be afraid of it. You wish you heard these things about math when you started calculus. Yes, scared you of complex integration and this and that. I believe that science should not be to challenge you to solve complex things. To me, the most important thing is to understand the concepts and then make use of them to build new products, come up with new inventions, new discoveries, new contributions. It's not by making you burden with the complexity of math and the other sometimes extremely irrelevant formulas to your field of study. So here, since this is hard to obtain, we move to the frequency domain. There is a saying, if you cannot find something in one domain, you move to the other domain. If it's in time is hard, most probably when you transfer to the frequency becomes easier. And what do we have here? What do we have here? MGF. What's MGF? Moment generating function, which is the Fourier transform of the PDF. You can the PDF you found in time domain, you can take it to the frequency domain, and in there, if you have here multiplication or if you have summation, you get multiplication. If you have, so it simplifies your solution, and you are able now to find a closed form solution to your bit error rate. Is that up until now? So far, we are good and fine. Yes, I think what we said about receive diversity applies to transmit diversity. If you have multiple receive antenna, you can say at the transmitter, I have multiple transmit antenna. If you use selection combining at the receiver, you can use it at the transmitter by measuring the channel. I am assuming you know the channel at the transmitter. If you use maximum ratio combining at the receiver, you can use maximum ratio combining at the transmitter. So with channel knowledge, when you have the channel knowledge similar to receive diversity, you can provide diversity gain. Without channel knowledge, you can obtain also diversity through proper design at the transmitter. What we call it Alamotti code. Alamotti code says that you assume that you have two antennas at the transmitter, and you want to provide full diversity from these two antennas without the knowledge of the channel. But you must guarantee that these two antennas experience independent deep fades, independent fading. So you transmit your first signal from here, x1, and you transmit your second signal from here, x2. And in the second round, you transmit here x1 conjugate, and here x2 conjugate multiplied by minus. If you design your system in this way, you can be sure all the time that you get full diversity gain too. But what's the drawback of this? The drawback of this is you are not transmitting the full rate. For example, when you have two antennas, you have the opportunity to transmit two data streams. But you have two antennas, and in two time slots, you are transmitting only two symbols. You must transmit four. Two antennas, two time slots, four symbols, different symbols you can transmit. But if you transmit four different symbols, your bit error rate will be something like this. But if you transmit with this technique, your bit error rate is this. Which one is better? The application decides. Do you want better bit error rate or better throughput? In case you are using SMS, you want better bit error rate. In case you are using voice or video, you want throughput. That's the thing. To transmit antenna, we call this technique something like, this is Alamuti code, but Alamuti code only works for 2 antennas. For more than 2 antennas, you need to bring a new design called space-time block coding. Why do we call them space-time? Because the antennas in space and the symbols in time. You have also frequency time, space frequency. This is in the case of using OFDM. Works over 2 consecutive symbols, I just explained here, achieves full diversity gain, no array gain. Part of various wireless standards, including LTE, is using it. LTE is using it. It's very hard to generalize it to more 2 antennas, but it's possible. There are new research. There are many available papers that can generate full diversity for 4 and 8, but it's a little bit, you need to use special type of coding. And this technique, we'll call it Alamuti coding. Alamuti coding, should I tell you the story of Alamuti coding? Who's Alamuti? Is a master student like you from Canada. He's originally from Iran. He went to Canada, studied master, and then he came up with this technique during his master. And the technique was published in 2000. Maybe 4 or 3, not sure, but it gained too much attention. Symbol, he's named it Symbol Diversity Technique. Symbol, he said symbol in the title of the paper. The paper, I think, has more than 13,000 citations by now. He moved after his graduation, he built a company with his friends, that he patented the idea and made a company around this idea. And now this technique is used in most wireless communication systems. With LTE, 3, I don't think 3G, LTE, 4G, it's very profound, very critical. MIMO that time was very new, people didn't study too much about it. His professor was working latest thing on the literature. So sometimes it's luck, sometimes also. It's very simple, not really difficult. The way he did it, really, by trial and error, it seems. He found this combination. When you send this combination, you get full diversity. Any other thing, you don't. So he got this idea, he kept trying, or many failures, until he get the optimal performance, and then published it. It was a very great contribution to the literature. And then, since then, he didn't even complete his PhD on this, because he already contributed something that enables him to build a business and make money for his life. You know, patent things. If your patent is used in a product, keeps producing money for you for the rest of your life. You don't need to work. But just think, push yourself a little bit, work hard for 1-2 years, produce something novel, produce something of value so that you get relaxed for the rest of your life. But usually we prefer to go with the other route. We prefer to work hard for whole our life, producing non-significant things. Yes, unfortunately, that's why our salaries are always very low, because we are not contributing. Just to produce one thing good, so that you get money while you are not working, yes? I'm motivating you because he is master student, like you guys. And wireless, you are in wireless too. I hope you enjoyed the story of Alamuti. I like the inspiration story like this, yes? Like you guys, believe in yourself, and we can put you on the edge. We have ideas, we have this, we can try to put you, yes? But I want students who believe that they can do this, they can challenge themselves, who believe that I want to be a master of myself in the future. I don't want to keep working hard till I die. And even my saving will not be enough for me when I get old. Yes? I want to, during my youth, I want to work like hell. produce something novel, make a pattern, make something astonishing, groundbreaking, and let's put it there, patent it. I will show you if you are interested. I can give a lecture about how to do that, and then in the future you never guess what the future is. It might not receive any attention now, but 5 years from now, 10, it might get something. So this is what I wanted to say, and with this we conclude our lecture, and by summarizing the main points we have learned. First, diversity overcomes fading effects by combining fading paths coming from different directions. Typically entails penalty in rate or bandwidth or complexity or size. As I just explained in Alamoti, I said you could have 4 symbols, but he is interested in reliability, enhancing reliability. Selection diversity picks path with highest SNR. This is what we call it, selection diversity. Maximum ratio combining co-phase the different signals and combine them coherently. The gain can be from 20 to 40 dB. Selection combining around 20 dB. MRC gives you the optimal gain actually. If you were to ask me which combining technique is the best, MRC. Analysis of MRC simplified using moment generating function by analyzing the performance in the frequency domain, not in the time domain. Transmit diversity with channel state information at the transmitter is same as receive diversity when you have the channel information, because the receiver as well has the channel information. And you can obtain diversity gain even without channel information at the transmitter by using Alamoti codes or space-time block codes. Besides, I mentioned in the presentation that massive MIMO is a perfect solution to combat fading. How does this work? When you have antenna, when you have base station here and you have one user talking to the base station, you have here 2,000 antenna. Let's say in the future, we didn't reach to that number, but basically we have 200. Up until now, people are able to design 200. This, you set the user, Internet of Things, send his signal to the base station. The base station receives the signal from the 200 antennas. Imagine 200 different channels. When you co-phase them using MRC, you know what you get? You get almost very near to 0 probability in error due to fading. You know what this means? This means that the fading term gets cancelled. That's a very amazing thing. With MIMO, any technique that was limited with noise or interference or fading, like some techniques, when you put it in MIMO, it doesn't get affected by these impairments that we experienced before. This is the beauty of massive MIMO. So with this, we conclude our lecture, and thank you very much for your attention, and we meet in next lecture.